This project is about Bach choral generation, but the main contribution is not only a model result. The title highlights the real story. Classifier-free guidance initially looked harmful, and only after auditing the sampler did the conclusion change. This is for CSE253, Machine Learning for Music, with Professor Julian Macaulay. The project covers 2 assignment tasks with 1 shared implementation. We start from JSB chorales, keep strict 4-part SATB examples, tokenize each frame in a chord first order, and train 1 decoder transformer. At generation time, the same backbone supports 2 outputs, an unconditioned chorale and a soprano conditioned harmonization. The structural and range masks are not separate models, they are decoding constraints that keep the MIDI schema valid and keep voices in plausible registers. The important setup is that task 1 and task 2 are not 2 disconnected systems. The evaluation story in task 2 builds directly on the same model and sampler used for task 1. This slide orients the peer reviewer against the assignment rubric. For each selected task, I need to cover data exploration, modeling, evaluation, and related work. I will avoid repeating the same dataset story twice, because task 2 uses the same JSB corpus, but changes the prediction problem by treating soprano as the condition. The evaluation section for task 2 is the center of the talk, so I will spend more time there than on routine implementation details. The dataset is small, so leakage control matters. We use the Music 21 JSB chorales, filter to strict SATB chorales in 4/4 time, and get 321 pieces. The split is hash-based and happens before transposition augmentation, which prevents augmented copies of the same chorale from appearing in both train and validation or test. After transposition, we have 4,865 training examples. This is not a huge corpus, but it is exactly aligned with the musical setting. 4 voices, short phrases, and Bach-style harmonic motion. This piano roll makes the representation concrete. SATB music is structured. Soprano, alto, tenor, and bass occupy different pitch ranges, and the voices move together in a constrained way. That is why we do not rely on unconstrained token sampling alone. The pitch class and density plots show that the corpus is also not uniform. It has real harmonic and rhythmic biases. The same structure will matter later when I discuss why structural masks and range masks are part of the experimental setup, not just output cleanup. Each frame is emitted in a fixed schema: bar, position, chord, then soprano, alto, tenor, and bass. The chord first decision is deliberate. It gives the model harmonic context before it predicts the voice tokens in that frame. We also considered more generic Remy-style event tokenization, but for this assignment, the chord first SATB schema gave a cleaner path to valid 4-part output. One important caveat is that the chord token helps language modeling, but it does not automatically solve voice leading. That distinction becomes important in task 2. The model is a small, modern decoder transformer. 6 layers, dimension 256, 8 attention heads, and about 6.34 million parameters. Within the assignment budget, the goal was not to scale the model as much as possible, but to build a reliable, symbolic music pipeline. I use standard modern components such as rope, RMS norm, SWIGLU, EMA weights, and bfloat 16 training. 2 planned deviations are worth mentioning because they change validation behavior. Curriculum masking was disabled because it created a train validation mismatch under short training. The loss was also extended to structural tokens because an autoregressive decoder must learn the schema tokens, not only the notes. This is the main task 1 quantitative result. All NLL values here are in bits per token. The uniform, unigram, and bigram baselines are useful because they separate vocabulary size, marginal pitch and token frequency, and short local transitions. The transformer reaches 0.800 bits per token, with the final CFG dropout 0.10 checkpoint. Compared with the Bigram baseline, that is about a 79% reduction in NLL. I would not compare this raw NLL directly to every published paper because tokenization schemes differ, but internally it shows that the model learned much more than local token statistics. The sampling result was a surprise. After fixing the typical filter bug, plain multinomial sampling at temperature 1.0 gave the best tested combination of parallel fifth rate and distinct 3 diversity. My interpretation is that the model distribution is already fairly concentrated. Extra filtering can remove tokens that are low probability but still musically valid, which may hurt diversity and sometimes the voice leading metric. The main lesson is that the sampler is part of the model behavior we evaluate. These papers are useful reference points, but they are not directly comparable by raw NLL. RNN NADE is an early neural baseline for polyphonic music, deep buck and coconut frame buck style generation as conditional sampling or infilling. Music transformer is important for relative attention in symbolic music, and TonicNet is especially relevant because it emphasizes feature-rich, chord-aware sequence design. The comparison I want the reviewer to take away is conceptual. Our work sits in this symbolic music line, but our exact token schema and evaluation protocol are different. Test 2 uses the same corpus from a different angle. Instead of asking the model to generate all 4 voices freely, we hold out a soprano line from a test chorale and force the soprano token at every soprano slot. The model then fills in alto, tenor, and bass. The final submission uses a held-out BWV 40.8 soprano. This makes the task a harmonization problem. Can the model produce a plausible 3-voice accompaniment while following a fixed melody? This slide shows how classifier-free guidance is implemented for harmonization. The conditional path sees the true soprano. The unconditional reference replaces the soprano with mask S. At inference, we combine the 2 logits as 1 plus W times the conditional logits minus W times the unconditional logits. For the final conditional output, W is 2. The 2 paths are batched together, so we do not pay for 2 fully sequential forward passes. The chord first ablation also matters here, removing chord first hertz validation NLL by about 0.17 bits per token, but it barely changes the voice leading metrics. So chord first helps the language model, not automatically the harmony rule we care about. The first CFG result looked bad. Our success criterion, SE2, was simple. When we use CFG, the generated harmonization should have fewer parallel fifths, but in the first measurements, W equals 2 made the parallel fifth metric worse at every CFG dropout value. At this point, the conservative interpretation was that CFG was amplifying a conditional preference that was not aligned with voice leading. That would have been a reasonable negative result, because the model it trained with token likelihood, not an explicit voice leading loss. This slide is a reminder to be careful with explanations that sound plausible. The structural failure story fit the model. Likelihood improved, but there was no direct penalty for parallel fifths, so CFG could easily push the wrong musical behavior. And the problem is that a coherent explanation is not the same thing as a correct measurement. Before writing that conclusion into the report, we needed to audit the evaluation path, especially the sampler. This is the bug that changed the interpretation. Typical sampling computes probabilities, log probabilities, and an entropy term. When structural or range masks introduce negative infinity logits, the entropy calculation can produce Nyan if it is not handled carefully. That broke the typical set and made the typical plus range path behave like the wrong distribution over the allowed vocabulary. The bug was easy to miss because not every sampler used this path. greedy, nucleus, and multinomial control rows did not fail in the same way. The key point is methodological. If the sampler silently changes the distribution, the model quality conclusion can be wrong, even when the training code is fine. This is the most important slide in the presentation. After fixing the sampler, the conclusion changed. For CFG dropout 0.10, CFG now moves the parallel fifth metric in the expected direction from 4.833 at W equals 0 to 4.615 at W equals 2. But the result is not simply that CFG always works. At CFG dropout 0.20 and 0.30, the same monotonicity criterion still fails. So the honest finding is narrower and more interesting. In this small symbolic model, CFG behavior is sensitive to the training dropout, and increasing dropout did not make guidance stronger. This is the central methodology story. The audit did not just clean up a number, it flipped the scientific conclusion. The final outputs use the remeasured configuration. CFG dropout 0.10, multinomial sampling, structural and range masks, and conditional CFG with W equals 2. The listening comparison is short. First the Bach reference, then the unconditioned sample, then the conditioned harmonization. I would not claim these are Bach quality outputs. The files are valid 4-part MIDIs, but the voice leading metrics still show a large gap. The point of this final configuration is that it follows the corrected evaluation result rather than simply choosing the lowest validation NLL. The related work gives two contexts. In harmonization, Deepback and Coconnet use different sampling or infilling machinery, and new acquire models use chord conditioning or relative attention. In guidance, Ho and Salimans introduce classifier-free guidance. Sanchez and colleagues studied it for autoregressive language models, and MusicGen uses conditioning in autoregressive music generation. Our result does not overturn that literature. It is a small model symbolic music caution. Condition dropout and sampler details can interact in non-obvious ways, so the evaluation path needs to be audited. To summarize, the parts that worked were chord-first tokenization, a compact modern transformer, structural and range masks, and CFG at CFG dropout 0.10 after the sampler fix. The main surprises were that typical sampling underperformed after the bug fix, and that higher condition dropout did not improve the SE2 criterion. The limitations are real, the model is small, training is short, and each ablation uses limited seats. The next step would be a voice-leading aware objective and a formal listening study. The final takeaway is the one I want the reviewer to remember. In empirical music machine learning, the sampler is part of the scientific claim.